Chapter 1. Introduction. Why Engineering Changed the World. Imagine a world without bridges, roads, machines, or electricity. A world in which people shape their lives with their bare hands, without the knowledge of tools, constructions, or technical systems. This is exactly how the history of mankind began, and this is exactly where the history of engineering begins. Engineering is much more than just the application of technology. It is the art of turning ideas into tangible reality, the combination of imagination and knowledge, of courage and precision. Engineers have been around for as long as there have been people who not only accept problems but also look for solutions. It was clear from an early stage that anyone who has mastered the understanding of natural forces, materials, and structures has power. Power over the construction of cities, over the design of landscapes, over the movement of goods and people. Engineering means bringing order to chaos, making the invisible visible, and creating possibilities that were previously unthinkable. From the first wheel to the great aqueducts of the Romans to the huge machines of our time, there is a common thread. The history of mankind is also the history of engineers. But engineering is not a straightforward path, but a multi-layered network. It arises from curiosity and necessity, from the search for comfort and from the pressure of survival. In times of peace, engineers create bridges, harbors, and cathedrals, and in times of war, they develop weapons, fortresses, and machines for destruction. Their role is therefore ambivalent. They stand for progress and hope, but also for power and threat. Over the centuries, the image of the engineer changed. The anonymous craftsmen who created nameless buildings became personalities revered as geniuses and symbols, from Archimedes to Leonardo da Vinci. Later, the engineer emerged as a profession in its own right, with training, responsibility, and social influence. Today, engineering encompasses countless disciplines: construction, mechanical engineering, electrical engineering, chemistry, computer science, and reaches into the farthest corners of our everyday lives. When we look at the history of engineering, we travel through the great stages of humanity: the civilizations of antiquity, the invention of tools and machines, the architecture of antiquity, the Middle Ages with its Gothic cathedrals, the Renaissance as an epoch of inventiveness, the Industrial Revolution as the turning point of an entire world, and finally the age of globalization, in which engineers created megacities, aircraft, and space technologies. Each epoch produces its own challenges, and each epoch leaves traces that we still see today. This script aims not only to enumerate buildings and inventions, but to form a narrative of people who had the courage to make the impossible possible. Engineers are designers of reality. Her works are bridges in the literal and figurative sense. They connect places, times, people, and ideas. Without them, the world we live in would be inconceivable. The following chapters are therefore a journey through the history of engineering. We start in Mesopotamia, where the first cities were built, and people began to dominate their environment with technology. From there, the path leads to Egypt, to the pyramids and temples, on to ancient Greece and Rome with their mathematical and architectural masterpieces. We follow in the footsteps of Arab scholars, the Gothic master builders of Europe, the visionaries of the Renaissance, and the pioneers of industrialization. Finally, we get to the present and take a look at the future, where engineers are opening up new horizons with artificial intelligence, sustainable energy, and space travel. It is a story of visions and setbacks, of triumph and error, of triumph and responsibility. Above all, however, it is a story that shows that engineering is much more than technology. It is the expression of human creative urge, the will to understand the world and to change it. Chapter 2. The Beginnings. Engineering in Mesopotamia and Egypt. The history of engineering begins where people became sedentary. When the hunter-gatherers gave up their nomadic way of life and founded the first settlements in the fertile soil of Mesopotamia and the Nile Valley, a new need arose: order and structure on a large scale. Agriculture demanded irrigation systems, cities for protective walls, temples for monumental design. The simple hut became a house, the village became a city, and with each new challenge, the need for technical knowledge grew. In Mesopotamia, between the Euphrates and the Tigris, the cradle of civilization began. It was here that the Sumerians invented not only writing, but also an early form of engineering. Their greatest achievement was the irrigation system, without which the land would not have been fertile. Canals, locks, and dams channeled the water into the fields and enabled surpluses, which in turn favored the emergence of cities, such as Uruk or Yar. This work was not an individual action, but required planning, organization, and cooperation, the first signs of what we now call an engineering achievement. Architecture also had its beginning in Mesopotamia. The ziggurats, those mighty stepped temples, rose above the cities like stone mountains. They were not only religious monuments, but also technical masterpieces. Using mud bricks, bitumen as a binder, and geometrically clear structures, the Mesopotamians created structures that lasted for thousands of years. The engineer of that time was usually a priest or royal architect who fulfilled religious and practical tasks at the same time. Technology and faith were inseparably linked. While in Mesopotamia the water was tamed and channeled in canals, the Egyptians used the power of the Nile. Year after year, the flood brought fertile mud, but it also threatened chaos and destruction. Only with precise knowledge of water levels, times, and the construction of canals could the river be controlled. This is where an initial engineering spirit became apparent: the combination of observation, calculation, and practical implementation. The most visible symbol of Egyptian engineering are the pyramids. To this day, they are considered the epitome of human creativity. More than 4,000 years ago, the Egyptians built buildings of a precision and dimension that amaze us even with modern technology. Millions of stone blocks, perfectly aligned with the cardinal directions, were moved with logistics whose secrets are still being debated. Whether ramps, levers, or sleds, the Egyptians knew techniques that made the seemingly impossible possible. But Egypt's engineering was not limited to monuments. Temples, tombs, obelisks, and the massive columned halls of Karnak and Luxor bear witness to an architecture that dominated not only size, but also richness of detail. In addition, the Egyptians developed early knowledge of mechanics and mathematics. Their measuring instruments, leveling devices, and ropes for determining angles were forerunners of modern engineering instruments. Water also played a central role here. Farmers used shadoufs, those simple lever devices to lift water from the Nile onto their fields. Later, more complex systems were added, which laid the foundation for hydraulic technology. The Nile was both a challenge and a gift, and Egyptian engineering was the answer to this dual nature. The organization of such large-scale projects is also remarkable. At that time, engineers in today's sense were royal officials who instructed workers, craftsmen, and architects. They planned not only buildings, but also their logistics, transporting stones over hundreds of kilometers, coordinating labor, supplying food and tools. Here, for the first time, a characteristic was shown that still distinguishes engineering today: the view of the whole, the merging of knowledge and resources. In Mesopotamia and Egypt, engineering began as a response to elemental needs: protection from the vagaries of nature, the creation of habitat, and the expression of religious power. But from these beginnings developed a knowledge that went far beyond the practical. It was here that foundations were laid, in geometry, in hydraulics, and architecture, that were to be taken up and further developed by later civilizations. Thus, Mesopotamia and Egypt mark the beginning of a journey that will accompany engineering for thousands of years. From the first canals and pyramids to the modern megabuildings, one line runs: the unwavering will of man to shape his environment. Chapter 3: Greeks and Romans, Ancient Masterpieces of Technology. When we talk about engineering in antiquity, we inevitably think of Greece and Rome. Both cultures have left behind not only monuments that survive in stone to this day, but also ideas that form the basis of modern engineering. While the Greeks excelled above all in theoretical thinking and mathematics, the Romans were the great practitioners who turned visions into reality. Together, they created a legacy that shaped technical progress for centuries. The Greeks were philosophers and mathematicians, but many of them were engineers at the same time. Names such as Archimedes or Heron of Alexandria are symbols of this combination of theory and practice. Archimedes designed screws to lift water, developed war machines, and formulated laws of mechanics that still apply today. With his aeolipile, Heron built a kind of early steam engine, which was never used practically, but shows how far the imagination could reach. In addition, architecture flourished. Temples such as the Parthenon in Athens testify to a precision and harmony that would not have been conceivable without sophisticated technical knowledge. The Greeks combined beauty with statics, philosophy with geometry, an ideal that later served as a benchmark. But as ingenious as the Greeks were in theory, it was the Romans who made engineering the actual discipline. Rome was a civilization of the organization, and its engineers were at the service of an empire that could not have existed without technology. Roads, bridges, aqueducts, and fortifications crisscrossed the Roman Empire and connected people, goods, and ideas. The famous sentence, "All roads lead to Rome," is no coincidence, but an expression of a tremendous engineering achievement. The Roman roads were more than just paths. They were works of art made of layers of gravel, sand, and stone slabs, built so precisely that some are still in use today. Bridges made of stone and concrete spanned rivers and withstood for centuries. The Romans were masters at using materials, especially concrete, which they mixed from lime, volcanic ash, and water. This material opened up completely new possibilities. Domes, arches, huge buildings such as the Pantheon in Rome, with its dome that is still impressive today. Another masterpiece were the aqueducts. They carried water from the mountains to the cities over hundreds of kilometers, with a minimal gradient, calculated so precisely that the water flowed steadily. The aqueduct of Pont-du-Gard in the south of France, or the water pipes to Rome, are testimony to this precision. Clean water meant life, hygiene, prosperity, and at the same time was a symbol of Roman power. Engineering was also indispensable in the military sector. Legionnaires built camps, bridges, and fortifications in a very short time. Siege engines such as catapults, ballistae, or battering rams were manufactured according to precise plans and made the Roman army almost invincible. This showed the pragmatic side of Roman technology. Efficiency and reliability took precedence over theoretical elegance. Perhaps the greatest legacy of the Romans, however, was the linking of technology with administration. Engineers were officers, civil servants, professionals who worked in a hierarchical order. Buildings were planned, costs calculated, workers organized, structures that are still typical of engineering today. When we look at Greeks and Romans together, we see two sides of the same coin. The Greeks provided the intellectual foundations, mathematics, geometry, mechanics, the pursuit of harmony. The Romans created a practical system from these foundations which supported a world power. Together, they laid the foundations on which the Middle Ages and the modern age could continue to build. At the end of this epoch, there remains a legacy that is visible not only in ruins, temples, and streets, but in ways of thinking, methods, and concepts. Anyone who plans a bridge or constructs a building today is, consciously or unconsciously, building on principles that were developed 2,000 years ago. The Greeks and Romans have shown that engineering is not just the art of building, but a cultural achievement that can sustain entire civilizations. Chapter 4. Engineers in Ancient China and India. While the Greeks and Romans created their masterpieces in the Mediterranean region, two other advanced civilizations developed in Asia whose engineering achievements are just as impressive: China and India. Over thousands of years, both civilizations developed independent traditions that not only shaped the lives of their societies, but also produced inventions that would later change the entire world. In China, engineering has always been closely linked to the idea of order and harmony. Even the first dynasties had huge irrigation systems built to tame the unpredictable floods of the Yellow River. The construction of dams, canals, and locks was a constant challenge and made engineers central figures in the state. One of the most famous early hydraulic engineering projects was the Dujiangyan irrigation system, which was built in the 3rd century BC. With its canals and weirs, it directed the water so skillfully that flooding was prevented and fields were reliably irrigated, a system that is still partly in use today. But Chinese engineering went far beyond hydraulic engineering. The construction of the Great Wall of China, which continued for centuries, shows the organizational power and technical sophistication that the dynasties were able to mobilize. Millions of workers moved stones, earth, and wood to build a bulwark against invaders that stretched thousands of kilometers through mountains and valleys. Even though many workers remained nameless, the planning of such buildings was a masterpiece in logistics, material science, and statics. China was also a country of inventors. This is where paper, the compass, gunpowder, and letterpress printing were created, all inventions of enormous engineering importance. Many of these developments were initially practical tools that then became revolutionary tools of civilization. The compass, originally used for divination, became a navigational instrument that enabled seafaring in completely new dimensions. Gunpowder, initially developed for fireworks, later changed the face of warfare worldwide. The Chinese were also pioneers in mechanics. Water meters, gears, complex automata, and finely crafted bronze casting techniques demonstrate a deep understanding of materials and forces. Some scholars and officials, such as Zhang Heng, who constructed a seismograph in the 2nd century AD, embodied the image of the engineer as a scientist and practitioner at the same time. At the same time, India developed its own traditions, which were strongly linked to religion, mathematics, and astronomy. As early as the Indus culture, thousands of years before our era, highly developed cities such as Mohenjo-daro and Harappa emerged, which had sophisticated sewage systems, orderly road networks, and standardized brick buildings. Here, the ability to design housing estates according to planning principles became apparent early on, an approach that continues to have an impact on urban planning today. Water also played a central role in India. Reservoirs, cisterns, and stepwell buildings ensured supplies in the arid regions. These stair fountains were not only technical but also aesthetic masterpieces, ornately decorated structures that combined water storage with architecture. In the field of mathematics, Indian scholars laid the foundations that became indispensable for engineering. The decimal system and the zero, which were developed in India and later transmitted to Europe, created the basis for calculations that are indispensable in buildings, machines, and later in modern technology. India's architecture also shows impressive feats. Temples with huge stone domes, palaces that represented entire dynasties, and precisely aligned observatories that translated astronomical knowledge into stone. Here, religious symbolism was combined with mathematical precision. In both China and India, engineering was not just a practical craft, but an expression of a worldview. Technology was supposed to create order in harmony with the forces of nature or as a mirror of cosmic principles. While in the West, the competition between man and nature was often in the foreground, these cultures emphasized the harmony of man, nature, and the cosmos. But their inventions were not limited to Asia. Many ideas reached the West via trade routes such as the Silk Road. Paper and compass, numbers and building forms traveled through the centuries, were adapted, changed, and finally shaped the development of global engineering.
China and India showed the world that engineering does not only mean monumental buildings, but also quiet but momentous inventions. A canal that feeds a city, a sign that allows calculations, a compass that brings ships safely to their destination. In these cultures, engineering took on a form that can still be felt today.
Chapter 5. Engineering in the Middle Ages. Castles, cathedrals, hydraulic structures. The Middle Ages are often described as a time of stagnation, an epoch between antiquity and the Renaissance in which knowledge was preserved but hardly anything new was created. But a closer look shows that the Middle Ages produced a wealth of innovations, especially in engineering. It was an era in which technical solutions for the safety, faith, and everyday care of people were in the foreground. Castles and cathedrals, mills and waterworks, they all bear witness to the fact that the art of engineering flourished during this time. The castles are perhaps the most recognizable symbol of medieval engineering. They arose not only from the need for splendor, but above all from the need to offer protection. With the collapse of the Roman Empire and the uncertain conditions in Europe, the castle became the center of power and security. Engineers and builders developed fortifications that could withstand attacks. Thick walls, towers, drawbridges, and moats. Each generation refined the techniques, from simple wooden castles on hills to massive stone castles like the Croix de Chevalier in the Middle East. Here, military technology was combined with logistics. Supply, water reservoirs, and escape routes had to be taken into account. At the same time, buildings of a completely different kind arose in the cities, the cathedrals. They are the marvels of medieval engineering, an expression of faith, community, and technical ingenuity. A cathedral often took centuries to build, and entire generations of engineers, stonemasons, and craftsmen worked on it. With pointed arches, ribbed vaults, and flying buttresses, they developed a system that allowed buildings to be erected at a height never achieved before. Light-flooded interiors, colorful glass windows, and filigree towers were only possible because engineers understood the forces of pressure and tension, even if they did not yet know the laws of physics in a modern form. Cathedrals such as Notre Dame in Paris or Cologne Cathedral still stand today as stone testimonies to this mastery. But the Middle Ages did not only show technical skill in the area of monumental buildings. The supply of water and energy has also been improved. Water mills and later windmills changed life fundamentally. They ground grain, operated sawmills, and helped with metalworking. Engineers developed paddle wheels, gears, and transmission systems that made mechanical energy efficiently usable. In a time without electricity, these mills were the engines of the economy. There has also been progress in hydraulic engineering. Canals connected rivers, made it possible to transport goods, and expanded agricultural land. Locks and weirs regulated the water level. Cities such as Venice or Bruges show how closely engineering and trade were linked. Without sophisticated hydraulic engineering, these centers of the Middle Ages would never have come into being. Another field was war and siege technology. Catapults, trebuchets, and siege towers reached a new dimension in the Middle Ages. Engineers worked on increasingly powerful machines to break through walls or storm cities. At the same time, castle builders reacted with ever stronger defensive installations. It was a constant race between attack and defense, with engineers on both sides using their knowledge. The role of the Islamic world in this epoch should not be underestimated. While Europe lost many ancient writings after the collapse of Rome, scholars in Baghdad, Cordoba, or Cairo preserved the knowledge of the Greeks and Romans and developed it further. They translated, commented on, and supplemented mathematical, astronomical, and mechanical writings. Water wheels, gears, irrigation systems, all of this was refined and later succeeded in returning to Europe, where there were new impulses. The engineering of the Middle Ages was therefore much more than a transitional phase. It laid the foundations for what would later unfold the Renaissance. In castles and cathedrals, in mills and hydraulic structures, technical knowledge was practically applied, tested, and passed on. It was an era in which engineers were not only master builders and craftsmen, but also carriers of knowledge that was passed down through generations. Today, when we wander through the ruins of a castle or marvel at the vault of a cathedral, we see not only architecture, but the result of centuries of experience, organization, and technical creativity. The Middle Ages may have been less marked by brilliant names such as Archimedes or Leonardo, but it was rich in quiet engineering achievements that still shape our image of Europe today.
Chapter 6: Arab and Islamic Engineering. While in the Middle Ages, Europe was still struggling with political upheavals, wars, and epidemics, the Islamic world experienced a heyday of science and technology. From Spain to Persia, from North Africa to India, a cultural network emerged that preserved, expanded, and enriched ancient knowledge with its own inventions. Engineering played a key role in this era, in the construction of cities and palaces, in the supply of water, in mechanics, and in science. At the center of this development were the great centers of knowledge: Baghdad with the House of Wisdom, Cordoba with its libraries, Cairo with its universities. Here, writings of the Greeks, Romans, Indians, and Chinese were collected, translated, and systematically studied. Arab scholars such as Al-Jazari, Al-Kindi, Al-Biruni, and Ibn Sina combined philosophy with practice, thus laying the foundation for what we know today as engineering. An outstanding figure was Al-Jazari, who worked in the 12th century. His work, The Book of Knowledge of Ingenious Mechanical Devices, described dozens of machines, water lifters, clocks, pumps, automatons. Many of his designs used gears, chains, pistons, and valves, elements that we recognize as precursors of modern machines. His water clocks became particularly famous, which not only showed the time, but often also set figures in motion. They were technical masterpieces and works of art in equal measure. Islamic engineering was characterized by a close connection between mathematics and practice. Al-Khwarizmi developed algebraic methods that simplified calculations and became indispensable for construction and astronomy. With precise measurements and geometric methods, maps could be created, cities could be planned, and buildings could be erected. The domes and minarets of the mosques, the palaces of Alhambra or Samarra, they all show a high degree of static knowledge and artistic creative power. Water played a central role in the Islamic world. In the often dry regions, wells, canals, and cisterns were vital. Engineers developed sophisticated systems to conduct water over long distances. Kanate, underground channels, transported groundwater over kilometers without it evaporating. Norias, giant water wheels, lifted water into aqueducts that supplied cities and fields. In cities such as Cordoba or Damascus, fountain courts and baths were built, which shaped not only supply, but also culture and hygiene. The Islamic engineers also left lasting traces in architecture. Their buildings combined functionality with aesthetics. Vaults and domes were built in increasingly daring shapes. Decorations with geometric patterns combined art with mathematics. The Great Mosque of Cordoba, the Mosque of Samarra, or the domes of Isfahan are examples of architecture based on precise engineering. The Islamic world also made a decisive contribution to the dissemination of knowledge. Many texts reached Europe via Spain and Sicily. Translations of Arabic works inspired European scholars of the Middle Ages and paved the way for the Renaissance. Algebra, astronomy, hydraulics. Without the mediation of Islamic engineers, Europe's technical awakening would hardly have been conceivable. But Islamic engineering was not just theory. It was closely linked to everyday life, supplying cities, improving agriculture, designing irrigation systems, developing clocks and equipment. Engineers worked for caliphs, sultans, and rulers, but their inventions shaped the lives of ordinary people as well. In this epoch, it becomes clear that engineering is always also cultural transfer. The Islamic world absorbed knowledge from India and China, combined it with Greek heritage, and created something new from it, which in turn flowed back to Europe. This combination of cultures and ideas is the particular strength of Islamic engineering. The Arab-Islamic epoch thus stands for a time in which engineers were not only master builders, but also mediators between East and West, between antiquity and modernity. Her works remind us that technology is never created in a vacuum, but is always part of a cultural exchange.
Chapter 7. The Renaissance, Leonardo da Vinci and the Rebirth of Technology. The Renaissance marked the beginning of an era in Europe that was characterized by new beginnings and curiosity. After centuries in which the knowledge of antiquity had been preserved above all and guarded in monasteries, a new spirit now unfolded, the will not only to understand the world, but to actively shape it. Art, science, and technology went hand in hand. At the center of this movement was also engineering, which experienced a heyday due to new ideas, inventions, and buildings. The Renaissance was characterized by faith in people themselves. The human being moved into the center. No longer God alone determined the perspective. This new attitude was reflected in art and architecture as well as in mathematics, mechanics, and architecture. Ancient texts that had returned to Europe from the Arab world were studied, translated, and applied. Scholars such as Galileo Galilei or Brunelleschi combined theoretical thinking with practical implementation. One of the biggest names of this era is undoubtedly Leonardo da Vinci. He was a painter, sculptor, anatomist, naturalist, and engineer. His notebooks, filled with sketches, calculations, and ideas, show a fantasy that was far ahead of its time. Leonardo designed flying machines based on the principle of bird flight, constructed early helicopters and parachutes, planned war machines, bridges, and canals. Much remained on paper, but his drawings show a way of thinking that explored the limits of what was possible. He understood that technology could be an extension of human abilities, flying, diving, lifting, destroying. But Leonardo was not alone. In Florence, Filippo Brunelleschi created the dome of the Cathedral of Santa Maria del Fiore, a building that is considered a masterpiece of engineering. Without scaffolding, only with ingenious wall constructions, he erected a dome of previously unimaginable size. His work combined mathematics, architecture, and material science in a revolutionary way. The Renaissance also produced new engineering achievements in warfare. Fortresses were now built according to geometric principles to withstand cannon fire. The so-called bastions, star-shaped structures with acute angles, were built all over Europe. Engineers were no longer only builders of cathedrals, but also designers of defensive structures. The invention of printing by Johannes Gutenberg around 1450 was another technical revolution. It enabled the mass dissemination of knowledge, and thus also of engineering ideas. Blueprints, sketches, and mathematical formulas could no longer be passed on orally or in handwritten manuscripts, but reached the whole of Europe in a very short time. Engineering thus became a discipline that could be discussed and standardized nationwide for the first time. Mechanics also experienced an upswing. Watches became more precise, gears more complex. Automatons, water pumps, and machines for mining and agriculture testify to a practical inventiveness. Engineers were no longer only concerned with buildings, but increasingly also with machines that made work easier or faster. The Renaissance was thus a time of rebirth, not only of art and philosophy, but also of technology. Engineers now came more to the fore. Their names became known, their works admired. They stood at the interface of science, art, and practice. Their buildings, machines, and designs laid the foundations for the centuries to come, in which engineering would play an increasingly important role in people's lives. When we think of the Renaissance today, we see images of paintings, sculptures, and magnificent buildings. But just as important are the sketchbooks, the mechanical models, and the bold ideas of those engineers who had the courage to think new things. They made technology a part of culture, an expression of human creativity, and an engine for the future.
Chapter 8. The Engineer as a Profession, From Master Builders to Specialists. With the Renaissance, a new spirit had awakened in Europe, but engineering was not yet an independent profession in the modern sense. Engineers were artists, architects, military men, or scholars who also solved practical problems. It was only in the transition to the early modern period that the engineer began to emerge as a profession in its own right, a development that was closely related to the growing demand for technical solutions and the professionalization of knowledge. Until then, the master builder was the central figure. He led cathedral or bridge construction, organized workers, drafted plans, and was familiar with materials and statics. His knowledge was often of a practical nature, handed down through experience and craftsmanship tradition. But the more complex the projects became, fortresses, canals, machines, cities, the clearer it became that a purely experience-based approach was not enough. The military in particular played a key role. With the advent of gunpowder and cannons, fortresses had to be rethought. Engineers designed star-shaped bastions, deep trenches, sloping walls, constructions that could withstand the bombardment. Rulers realized that they needed reliable technicians for their power. In France, the first schools for fortification were established, and engineers became officers of rank and responsibility. They were no longer just craftsmen, but part of the state power apparatus. At the same time, the need for infrastructure grew. Roads, bridges, canals, harbors, all of this required planning, surveying, and construction. Engineers were no longer only responsible for representative buildings, but for the lifelines of entire empires. The 16th and 17th centuries saw the birth of a new class of technicians who were increasingly systematically trained. The natural sciences played their part in this. With the scientific revolution, names like Kepler, Galileo, Newton, a new understanding of the laws of nature emerged. Mechanics, statics, and hydraulics could now be described mathematically. Engineers began to base their work on calculations, not just experience. They became mediators between theory and practice. They took the abstract formulas of science and translated them into bridges, machines, and buildings. The organization also changed. Engineers began to work in groups, hierarchies and responsibilities developed. Construction plans became more detailed, documentation more precise. The engineer was no longer just the ingenious master builder or artist, but part of a larger network that served state, military, and economic interests. The perception in society also changed. Engineers were regarded as specialists whose knowledge was valued but also feared. They could erect buildings but also construct weapons. Their skills stood for progress but also for power. It is no coincidence that many of them were in the service of kings and princes who wanted to secure fame and influence with technical projects. Slowly, the idea arose that engineering was a discipline in its own right, with its own rules, methods, and traditions. Although modern university education was still lacking, the first academies, especially in France and Italy, laid the foundation stone. The versatile master builder of antiquity and the Renaissance became a specialized expert, a process that was to reach its climax in the coming industrialization. Thus, this period marks a decisive step in the history of engineering, the transition from art to science, from the individual to the profession, from experience to calculation. The engineer became a recognized actor in the game of powers, in the construction of cities, in the progress of technology.
Chapter 9. Military Technology and Fortress Construction. Engineers in the Service of Power. Hardly any other area has shaped the development of engineering as much as the military. Since the first city walls of Mesopotamia and the Roman legionary camps, technology has been inseparable from power and defense. But with the advent of gunpowder and cannons in the late Middle Ages, the relationship changed fundamentally. Suddenly, centuries-old fortifications had become vulnerable. Towers and walls that once seemed insurmountable could be brought down by a few well-aimed projectiles. Engineers had to find new answers, and they did so with a mixture of mathematics, geometry, and practical ingenuity. This is how the bastionary system was born, which shaped the architecture of Europe for centuries. Instead of tall, round towers, flat, angular bastions were built that protruded from the walls like spearheads. This form made it possible to put the attacker in the crossfire from several sides. The ramparts were no longer built upwards but in width. Earth was used as a damping layer to absorb cannonballs. Ditches, redoubts, glacis, and outworks completed the system to form a veritable labyrinth of defensive lines. Engineers such as Sébastien Le Prestre de Vauban in 17th century France perfected this construction method. Vauban was not only an ingenious fortress builder, but also a master of siege technology. He drew up plans according to which attackers systematically dug trenches and trenches in order to approach a fortress step by step. His dual knowledge, in attack as well as in defense, made him a key figure. His fortresses, which were built throughout France, are still considered prime examples of military engineering today. But military technology was not limited to walls. Siege engines were further developed, cannons more precise, powder storage safer. The transport of troops and material required bridges that could be built in the shortest possible time. Engineers accompanied armies on their campaigns, built crossings over rivers, roads through swamps, fortifications in conquered cities. Their task was to secure the movements of the army. They were the silent but indispensable strategists in the background. The military also contributed to the institutionalization of the engineering profession. Many rulers founded special engineering corps in which knowledge was collected, standardized, and passed on. In France, the Corps des ingénieurs du génie militaire. In Prussia, the pioneer troops. These corps were schools and laboratories at the same time, places where experience and theory merged. Engineers now received training that systematically prepared them for their tasks. Military technology had an impact far beyond the battlefield. The geometry developed for fortresses was used in urban planning. Many Baroque cities with their star-shaped layouts were built according to the same principles. The construction of roads, which was necessary for troop movements, promoted trade. Bridges built for military campaigns remained and served civilians. Thus, engineering in the service of power was at the same time a motor for the development of society and the economy. Of course, this combination of technology and war also had its downsides. Engineers helped make wars more efficient, destruction more comprehensive, and sieges more deadly. Their creativity was not only at the service of progress, but also at the service of violence. This ambivalence accompanies engineering to this day, the ability to both build and destroy. But it was precisely this close connection with power and domination that gave engineering a new meaning in the early modern period. Engineers were no longer anonymous craftsmen, but advisors to kings and generals, part of the elite, equipped with knowledge that could make the difference between victory and defense. Thus, in this era, engineering became a discipline that was at the heart of political and military power. The fortresses, canals, bridges, and roads of the early modern period are not only architectural relics, but symbols of a time in which engineers helped determine the fate of entire nations.
Chapter 10. The Engineer and Early Science, Mathematics, Mechanics, Astronomy. With the transition to the modern era, two currents merged that decisively changed engineering. The practical experience of master builders and military engineers on the one hand, and the systematic study of the laws of nature on the other. Mathematics, mechanics, and astronomy became the foundations on which engineers now built their work more than ever before. This combination of theory and practice gradually turned engineering into a science. Mathematics played a key role in this.
The Egyptians and Greeks had already built with geometry, but now calculations became more comprehensive and precise. With the spread of Arabic numerals and the zero, tools were finally available that made complex calculations possible. Algebra and geometry gave engineers a foundation to plan buildings not only according to feeling or tradition, but according to clear formulas. Surveying, statics, proportions, all this could now be done on a uniform mathematical basis. The mechanics developed in parallel. Galileo Galilei, who is often considered the father of modern science, studied the falling of bodies, the rolling of balls, the effect of levers and obliques. His experiments were not just philosophical gimmicks, but directly relevant to engineers. They explained why bridges hold, how pulleys work, how projectiles fly. With mechanics, engineering received a set of rules that went beyond trial and error. Finally, Isaac Newton took this development to a new level. With his laws of motion and gravity, he provided engineers with tools that explained not only the mechanics of everyday life, but also the orbits of planets. Suddenly, it was possible to calculate how cannonballs fly, how water flows in canals, how forces act in buildings. Newton's Principia Mathematica thus indirectly became a textbook for engineers, who could now draw not only from experience, but from universal laws. Astronomy also played a role, even if at first glance it had less to do with technology. But anyone who planned cities, built canals, or navigated ships needed knowledge of stars and celestial movements. Precise calendars, navigation instruments such as the sextant or the compass, maps, they are all based on astronomical observations. Engineers use this knowledge to survey land, guide ships safely across oceans, or align structures exactly. During this time, engineers also began to focus more on machines in the narrower sense. Windmills and watermills were improved, pumps and lifts were designed more efficiently. Gears, screws, and pistons formed the basis for increasingly complex mechanisms. Many of these developments were due to the new scientific thinking, which no longer only described phenomena, but explained their causes. The institutionalization of this knowledge was also important. Academies, universities, and later technical schools began to train engineers systematically. Mathematics and mechanics became integral parts of the curricula. In this way, the engineer increasingly detached himself from the mere craftsman or artist and moved closer to the scientist. But despite all the theory, practice remained indispensable. Engineers had to build bridges, dig canals, design ships. And it turned out that calculations and reality did not always match. The engineer was thus a mediator between two worlds: the abstract formulas of science and the unruly materials of practice. It is precisely in this field of tension that its special significance developed. The early modern period was thus a phase in which engineering began to gain scientific depth. Mathematics, mechanics, and astronomy gave him new tools, but it was always the art of implementation that made the difference. The engineer became a designer between heaven and earth, in the truest sense of the word. Chapter 11. The Industrial Revolution 1. Steam engines, bridges, railways. With the beginning of the Industrial Revolution in the 18th century, engineering entered a completely new dimension. For the first time in history, technology was no longer only used selectively to solve individual problems, but it became the engine of a comprehensive social transformation. Factories, machines, and new energy sources are changing not only the world of work, but people's entire lives. Engineers were at the center of this upheaval. The driving force of this era was the steam engine. Although primitive forms had already existed before, it was not until James Watt in the late 18th century that the steam engine was decisively improved. With its capacitor and more efficient mechanisms, he made it a versatile machine. Suddenly, energy could be generated independently of wind, water, or muscle power. Factories no longer had to be located on rivers. Ships could go against the current.
Trains could cross entire continents. The steam engine was the key that opened the door to modern industry. With the availability of energy, the need for new machines also grew. Engineers designed looms, presses, pumps, locomotives. Each advance led to the next. Better tools enabled more precise machines, which in turn produced new products. It was a cycle of technical progress driven by engineers with inventiveness and practical knowledge. This change was particularly visible in bridge construction. Bridges had already spanned rivers in the Middle Ages, but now railways demanded new, more stable constructions. Engineers resorted to iron, a material that was stronger and more resilient than stone or wood. Bridges such as the Iron Bridge in England, built in 1779, were pioneers of iron construction. Later, enormous spans, suspension bridges, and viaducts followed, which shaped landscapes and opened trade routes. Engineers had to make new calculations to understand the forces of tension and compression in metals. Bridge building became a field in which theory and practice met directly. But perhaps the most spectacular achievement was the railway. It combined the speed of the steam engine with transport and changed the world like hardly any other invention. Rail tracks crisscrossed Europe and North America. Cities grew along the new traffic arteries. Trade and mobility took on unimagined proportions. The construction of railway lines required tunnels, bridges, stations, a gigantic field of work for engineers. They planned routes through mountains, designed locomotives, coordinated the deployment of thousands of workers. The railway was not only a technical but also a social project. It brought people closer together, shortened distances, and changed the sense of time. For the first time, time was synchronized in regions. Station clocks determined everyday life. Engineers were the silent architects of this new world in which space and time took on a different meaning. The power of the new technology was also evident in mining. Pits could be drained with steam pumps. Drilling machines penetrated deeper into the rock. Coal and ore provided the fuel and material for other machines. Engineers were at the intersection of these developments. They developed tools, planned shafts, improved conveyor systems. The Industrial Revolution was thus more than a sequence of inventions. It was a profound change in which engineers were given a new role. They were no longer just craftsmen or builders, but designers of industrial society. Their work determined how factories functioned, how cities grew, how people traveled. With the steam engine, bridges, and railways, a new era began that irrevocably changed the world. The engineer became a symbol of progress, the embodiment of an optimism that believed that technology could solve all problems. But this belief was also to be put to the test in the coming decades.
Chapter 12. The Industrial Revolution II. Steel, Electricity, and Chemistry. The first phase of the Industrial Revolution was characterized by coal, steam, and iron. But towards the end of the 19th century, a second wave began, which brought even more profound changes. Steel, electricity, and chemicals opened up new horizons, and with them, a modern world as we know it today emerged. Engineers were once again at the center of this development, as architects of the technical future. Steel was the new miracle material. While iron had already been used before, the Bessemer process enabled the cost-effective mass production of steel from the 1850s onwards. This material was not only stronger, but also more elastic than conventional iron. This made it possible to create structures that would have been unthinkable before. Skyscrapers, gigantic bridges, railway networks with ever longer spans. Engineers such as Gustave Eiffel made spectacular use of the new opportunities. His Paris Tower, built in 1889 for the World's Fair, was not only a technical masterpiece, but also a symbol of the triumph of engineering. At the same time, electricity conquered the world. Initially admired as a curiosity in laboratories, it soon became a practical source of energy.
Engineers developed generators, transformers, and lines that made it possible to transport electricity over long distances. Thomas Edison and Nikola Tesla were associated with two different visions: direct current versus alternating current. The electricity war ended with the triumphal march of alternating current, which proved to be more efficient. Electricity revolutionized lighting, communication, and propulsion. Street lamps illuminated cities. Factories worked independently of daylight. Trams and subways made urban mobility a new experience. Chemistry brought a third dimension to this upheaval. Engineers and chemists developed new processes for the production of dyes, fertilizers, explosives, and later plastics. All this changed agriculture, industry, and war in equal measure. Industrial chemistry made products that had previously been luxuries affordable, while at the same time enabling new materials that shaped everyday life. Engineers faced not only technical but also organizational challenges. Factories became larger, production processes more complex. It was no longer enough to build individual machines. You had to design entire systems in which energy, raw materials, and labor were coordinated with each other. With this, modern engineering also developed further, towards a discipline that dealt with processes and structures as well as with individual inventions. The architecture also changed. Steel girders allowed buildings to grow upwards. The skyline of cities like New York or Chicago bears witness to this change. The elevator, a comparatively simple invention, made high-rise buildings practical in the first place. Cities became vertical. Bridges spanned rivers of unprecedented lengths. Halls and railway stations were given gigantic roofs made of steel and glass. The Second Industrial Revolution was also a time of globalization. Railways crossed continents, steamships connected oceans, telegraph lines stretched across countries and seas. Engineers were the invisible architects of this networking, which shrunk the world. But with the new possibilities, the risks also grew. Explosives such as dynamite, developed for mining and the construction of tunnels, were soon used in warfare. Chemical products intended for agriculture and industry could also have a destructive effect. Engineers moved in a field of tension between progress and danger, between prosperity and destruction. By the end of the 19th century, the role of the engineer had changed fundamentally. He was no longer just an inventor or builder, but a professionally trained professional with social responsibility. Technical universities were created. Engineering associations formed networks. Trade journals disseminated knowledge. Engineering became a recognized profession and the driving force of a world that was changing faster than ever before. The Second Industrial Revolution brought steel, electricity, and chemicals, three pillars on which modern civilization rests. And it finally made the engineer a figure without whom the world was no longer conceivable.
Chapter 13. Engineers as Nation Builders. Infrastructure in the 19th Century. The 19th century was not only the age of industry, but also the century of nations. States were reconstituted, empires grew or crumbled, and in the midst of this political change, engineers played a key role. They were the builders of nations, because without roads, railways, ports, and telegraph lines, neither economic advancement nor political unity was possible. Infrastructure became a visible sign of progress, and engineers were its architects. An outstanding example is railway construction. In Germany, the expansion of the railway networks was considered a decisive factor in the founding of the German Empire in 1871. With lines connecting cities creating economic interdependencies and promoting trade. At the same time, they made it possible to transport troops quickly, a military advantage that strengthened political influence. Engineers planned routes, constructed bridges, built railway stations that became cathedrals of progress. In the United States, too, the railroad was the symbol and engine of the nation.
The completion of the Transcontinental Railroad in 1869 connected the east and west coasts. Engineers overcame mountains, crossed prairies, and spanned bridges over rivers. The railway opened up new settlement areas, made raw materials accessible, and contributed to the expansion of the country. A triumph of engineering that was also associated with the displacement of indigenous peoples and massive interventions in nature. Roads and canals also played a central role. The construction of the Erie Canal in the USA, completed in 1825, connected the Atlantic with the Great Lakes and revolutionized trade. In Europe, rivers have been straightened, locks built, and canals dug to supply industries and connect cities. Engineers were faced with the task of transforming natural landscapes into traffic arteries, a challenge that required not only technical skills, but also organization and foresight. Another field was urban development. Industrialization brought with it a massive population growth in the cities. Engineers had to build new roads, develop sewage systems, and ensure a water supply. Projects such as Joseph Bazalgette's London sewer system saved millions of lives by curbing cholera epidemics. Engineers have not only made cities bigger, but also healthier and more livable. During this time, engineers became symbolic figures of progress. They were no longer just specialists in the background, but were in the public spotlight. Engineering structures such as the Brooklyn Bridge in New York or the opening of the Suez Canal in 1869 became national and international events. The engineer was now not only a technician, but also a hero of progress who set entire nations in motion. With the professionalization of the profession, this trend intensified. Engineering associations such as the Association of German Engineers, VDI, or the Institution of Civil Engineers in Great Britain gave the profession a firm structure. Engineers exchanged knowledge, published in journals, and established standards that gained international validity. But the role of engineers as nation builders also had its downsides. Large-scale projects were often associated with high social costs, forced labor, exploitation of workers, and massive interventions in nature. Engineers became henchmen of colonial expansion, building railways and ports in Africa that served the interests of the colonial powers rather than the local populations. Despite these ambivalences, the 19th century remains an epoch in which engineering took on a new, central role in politics and society. Engineers not only built bridges and canals, but also connected regions, markets, and people. Her works were symbols of nation building, monuments of progress, and manifestations of state power at the same time. At the end of the century, it was clear that there was no modern nation without engineers. They were the silent legislators of infrastructure, the architects of a world that was changing rapidly.
Chapter 14. The Engineer in the Age of World Wars, Weapons, Planes, Tanks. The 20th century began with an unbroken belief in progress. Engineers had built bridges, modernized cities, brought electricity into homes, and led railways across continents. But with the outbreak of the First World War, another side of this progress became apparent. Engineering could not only create prosperity, but also destruction on an unprecedented scale. The two world wars became gigantic test benches of technology, and engineers were at the center of this development. In the First World War, conventional technology initially dominated: cannons, fortresses, trenches. But it soon became apparent that modern engineering would change the face of war. Machine guns, more precisely manufactured artillery, poison gas, all these were products of industrial production and engineering innovation. Trench warfare, which would have been inconceivable without engineers, was particularly formative. Miles of trenches, concrete bunkers, underground supply systems. The war was not only a battle of soldiers, but also a race of engineers who constantly developed new solutions for attack and defense. A decisive innovation was the tank. Originally developed in response to the problem of insurmountable trenches and machine guns, it combined the mechanics of the tractor with the protection of steel plates and the firepower of cannons.
British engineers introduced the first models in 1916, which still seemed clumsy, but laid the foundation for a completely new type of weapon. Aviation also came to the fore. Aircraft that were ridiculed as shaky inventions shortly before the war developed into militarily relevant machines in just a few years. Engineers designed more stable wings, more powerful engines, the first bombers and fighter planes. Mastering the skies became the new strategic goal, and thus the field for engineers who constantly devised improvements. The Second World War took these developments to an even higher level. Engineers worked on submarines, tanks, missiles, and aircraft whose performance exceeded the previous dimensions. German engineers developed the world's first ballistic rocket with the V-2 rocket, a forerunner of later space travel, but which was used as a weapon of terror at the time. The Manhattan Project was created in the USA, in which physicists and engineers jointly developed the atomic bomb, a technical masterpiece that also marks the darkest chapter in engineering history. The technology also reached new dimensions in aviation. The Spitfire, the Messerschmitt Bf-109, the Boeing B-17, or the Mitsubishi Zero, all these aircraft were products of the highest engineering art. They combined aerodynamics, lightweight construction, and engine technology at a level that was unthinkable just a few years earlier. With the jet aircraft, which was developed towards the end of the war, the next chapter in aviation history began. Tanks such as the German Tiger or the Soviet T-34 dominated vehicle construction. Their designs combined firepower, armor, and mobility in different balances, and they showed how decisive engineering superiority could be in the outcome of battles. The warfare of the first half of the 20th century was thus to a large extent an engineering conflict. States invested enormous resources in research. Engineers became strategic figures whose work could make the difference between victory and defeat. The war was industrialized, and engineers were at the forefront of this industrialization. But the world wars also showed the ambivalence of engineering. The same creativity that had previously produced bridges, railways, and water supply systems was now used for destruction. Engineers had to ask themselves to what extent they were responsible for the consequences of their work. This ethical question accompanies the profession to this day. At the end of the Second World War, the world was a different place. Engineers had proven that their abilities could unleash tremendous power, power that could destroy cities but also rebuild societies. The Cold War, which immediately followed, was intended to show that even in peacetime, engineers remained one thing above all: the designers of technical civilization, with all its opportunities and dangers.
Chapter 15. Engineering in the 20th Century. Modern Architecture, Cars, Airplanes. After the destruction of the two world wars, the world was faced with the task of reconstruction. Cities had to be rebuilt, infrastructures repaired, factories put back into operation. Engineers played a central role in this, and at the same time, a new chapter opened in which technology was no longer only geared towards war and armaments, but also towards mobility, prosperity, and modern ways of life. The 20th century thus became the stage for some of the greatest masterpieces of engineering in construction, architecture, automotive, and aircraft construction. The architecture of this era was characterized by the new materials, steel, glass, and concrete. Skyscrapers became symbols of progress. In the USA, high-rise buildings were built from the 1920s onwards that permanently changed the face of cities. The Chrysler Building and later the Empire State Building in New York demonstrated what was possible with modern engineering technology. Buildings that rose hundreds of meters into the sky, accessible by elevators and supported by skeleton constructions made of steel. The art of architecture also changed in Europe. Functionalism and modernism relied on clear lines, on the combination of aesthetics and technology. Architects such as Le Corbusier or Bauhaus engineers such as Walter Gropius worked hand in hand with technicians to create buildings that were not only beautiful but also efficient and practical.
Engineers developed supporting structures, facade constructions, and heating systems that revolutionized living and working. At the same time, the automotive experienced an unprecedented rise. From a luxury object for a few, it developed into a mass product. With the assembly line, Henry Ford introduced a production method that made cars affordable for broad sections of the population. Engineers improved engines, chassis, and bodies so that vehicles became faster, safer, and more reliable. The car not only changed mobility, but also the infrastructure. Roads, bridges, petrol stations, and entire cities were rethought to accommodate individual transport. Engineers also broke new ground in aircraft construction. The simple biplanes of the First World War became powerful machines that could fly over continents. In the 1930s, the first scheduled flights were established, and after the Second World War, the era of civil aviation began. The Boeing 707, later the Concorde or the Boeing 747 jumbo jet, made flying commonplace for millions of people. Engineers had to develop solutions for aerodynamics, lightweighting, engines, and safety, challenges that made the aerospace industry one of the leading fields of engineering. Engineers also changed lives in everyday life. Electrical household appliances, modern machines for agriculture and industry, new means of communication, all this was based on engineering developments. The refrigerator, the radio, the television, they were all not just inventions of tinkerers, but the results of systematic engineering work. Especially after 1945, the will to use technology for peace became apparent. Bridges and roads connected countries again, and the reconstruction of cities such as Warsaw, Coventry, or Hiroshima became the task of generations of engineers. At the same time, new symbols of modernity emerged. The Eiffel Tower, a relic of the 19th century, was joined by buildings such as the Golden Gate Bridge, the CN Tower in Toronto, or the Sydney Opera House, technical masterpieces that also became cultural icons. But 20th century engineering also had its downsides. Environmental pollution, resource consumption, mass transport, these were all consequences of technical expansion. Engineers increasingly saw themselves as responsible not only for building efficiently and innovatively, but also for acting sustainably and responsibly. The 20th century thus became an age in which engineers shaped the face of the modern world. High-rise buildings, cars, airplanes, factories, they are all expressions of an era that believed in technical progress and made it visible in all areas of life. The engineer became the designer of modern everyday life, the creator of a new civilization, the achievements of which surround us to this day.
Chapter 16. Electronics and Computers. New engineering disciplines emerge. While cars, airplanes, and skyscrapers shaped the visible face of the 20th century, an equally profound revolution took place in the background. Invisible, but no less effective, the emergence of electronics and computer technology. Here, a completely new branch of engineering developed, which was no longer based on steel and concrete, but on circuits, semiconductors, and information. The beginnings lie in the early 20th century. With the invention of the electron tube, electrical signals could be amplified and controlled for the first time. Radios, early televisions, and communication devices became possible. Engineers built circuits that transported speech and music across continents. Electronics expanded the scope of engineering into previously unknown dimensions. No longer only buildings and machines, but also information and communication became a task. A decisive step was the development of the computer. During the Second World War, the first mainframe computers, such as the ENIAC in the USA or the Zeus Z3 in Germany, were created. They were still room-filling machines, powered by thousands of tubes that devoured enormous amounts of energy. But they proved that calculations that previously took days were possible in seconds. Engineers and mathematicians worked closely together to make these machines work, a new alliance between theory and engineering.
With the invention of the transistor in 1947, the real computer age began. Transistors were smaller, more reliable, and energy efficient than tubes. Integrated circuits soon followed, combining thousands of components on tiny chips. Engineers developed computers that no longer filled entire rooms, but fit on desks, and eventually in pockets and palms. The 1960s and 1970s saw the birth of modern computer science. Engineers worked not only on hardware, but also on software, programs that controlled machines and opened up new fields of application. The calculating machines became tools for science, industry, administration, and finally, everyday life. Electronics also revolutionized other areas of engineering. Airplanes were given electronic controls, cars were given onboard computers, factories were automated. Communication technology brought the telephone into every home, and finally, worldwide networking with the Internet. Engineers designed networks, data lines, satellite connections, an invisible fabric that connected the world more closely than any railway or bridge before. Microelectronics also gave rise to a new type of engineer, the computer scientist and electrical engineer who did not work with stones or steel, but with data, algorithms, and electronic currents. This specialization changed the self-image of the profession. The engineer was no longer only the builder of material structures, but also the architect of virtual worlds. The electronics and computer technology of the 20th century have fundamentally reshaped the world. They not only brought forth new devices, but also new forms of working, learning, and communicating. Without this development, modern society with the internet, smartphones, and artificial intelligence would be unthinkable. This opened up a new dimension in engineering, one that went beyond the visible world and laid the foundations for the digital revolution of the 21st century.
Chapter 17. Space Travel, Engineers in the Race to the Moon. Hardly any other chapter in the history of engineering symbolizes the human urge for progress as impressively as space travel. What existed for thousands of years only in myths and dreams, the desire to leave the Earth and conquer the skies, became a reality in the 20th century. This was only possible thanks to engineers who developed rockets, constructed space capsules, and designed systems that could bring people safely into the cosmos and back again. The roots of this development go back to the first half of the 20th century. Rocket experiments by pioneers such as Konstantin Tsiolkovsky in Russia or Hermann Oberth in Germany laid the theoretical foundations. They described the principles of rocket propulsion, calculated trajectories, and showed that journeys into space would be possible with multi-stage rockets. What initially sounded like science fiction suddenly became tangible during the Second World War. The German V-2 rocket, designed under the direction of Wernher von Braun, was a weapon of destruction, but at the same time, the first missile to reach the border of space. After the war, the USA and the Soviet Union began to systematically develop rocket technology, driven by competition, politics, and the emerging Cold War. Engineers were now in the service of a race of systems. On October 4, 1957, the Soviets achieved their first success with Sputnik 1, a small satellite that sent signals to Earth and amazed the world. This moment marked the beginning of the space age. The reactions were tremendous. In the USA, Sputnik caused a shock that led to the founding of NASA. Engineers and scientists were given enormous resources to catch up. The space race was no longer just a technical challenge, but also a political symbol. Whoever ruled the skies proved superiority on Earth. On April 12, 1961, the Soviet Union set the next milestone. Yuri Gagarin became the first person to circumnavigate the Earth. Behind this triumph was the work of countless engineers who built a rocket strong enough, designed a capsule safely, and developed life support systems that survived the flight. The cosmos was no longer unreachable. The U.S. response followed with the Apollo program. Engineers were faced with tasks that can hardly be overestimated.
rockets of unprecedented size, navigation systems with the highest precision, computer technology that had to work reliably in tiny modules. The Saturn V rocket, designed under Wernher von Braun's leadership, was the most powerful launch system ever built. On July 20, 1969, mankind achieved its greatest dream to date. Neil Armstrong became the first man to set foot on the moon. It was a triumph for the engineers as well as the astronauts. But space travel was never just prestige. Satellites revolutionized communication, weather forecasting, navigation. Engineers developed systems that sent signals around the globe, supported agriculture, improved disaster preparedness. Missiles, once intended as weapons, became carriers of a new global infrastructure. Even after the end of the race to the moon, engineers remained active in space. Space stations such as Mir or the International Space Station, ISS, pose completely new challenges. Life for months in orbit, supply by space freighters, complex energy and climate systems. Every screw, every cable had to work, because a mistake could endanger the lives of astronauts. Space travel shows perhaps more clearly than any other field the complexity of engineering. It requires the highest precision, international cooperation, gigantic budgets, and at the same time, the courage to cross borders. Space engineers are bridge builders between dream and reality, between Earth and the cosmos. Today, the view has broadened. Not only states, but also private companies are engaged in space travel. Engineers at companies such as SpaceX, Blue Origin, and others are working to make space travel cheaper and reusable. The dream now extends further, to Mars, to asteroids, to permanent settlements beyond Earth. The history of space travel in the 20th century is therefore not just a technical chronicle. It is a story about man's unwavering will to make the seemingly impossible possible. Without engineers, this dream would never have become reality.
Chapter 18: Globalization and Engineering, Bridges, Skyscrapers, Megaprojects. The late 20th century marked the beginning of a new era in which technology not only reflected national ambition, but increasingly became an expression of a globalized world. Engineers were no longer just in the service of individual states, but worked on projects that connected continents, required international cooperation, and often became symbols of cosmopolitanism. Bridges, skyscrapers, and gigantic infrastructure projects shaped the image of a networked modernity. Bridges have always been masterpieces of engineering, but in the globalized world, they have reached dimensions that previously seemed unimaginable. Suspension and cable-stayed bridges spanned entire arms of the sea. The Akashi Kaikyo Bridge in Japan, opened in 1998, measures a span of almost 2 kilometers and defies typhoons and earthquakes, a triumph of engineering precision. Engineers have also made their mark in Europe. The Storebelt Bridge in Denmark or the bridge over the Bosphorus in Istanbul are not only traffic arteries but symbols of the connection between countries and cultures. The global character became even clearer in the construction of skyscrapers. While New York was long the capital of high-rise buildings with the Empire State Building and later the Twin Towers, the center shifted to other regions in the late 20th and early 21st centuries. The Petronas Towers in Kuala Lumpur, the Taipei 101 in Taiwan, or the Burj Khalifa in Dubai, the tallest building in the world at over 800 meters, embody the race for height, prestige, and technical sophistication. Engineers had to develop completely new systems, elevator technologies that extend over hundreds of floors, air conditioning systems for gigantic interiors, materials that are both light and strong. Mega projects became the new field of engineers. The construction of the Channel Tunnel between England and France, completed in 1994, connected two nations under the English Channel. Almost 40 kilometers of tunnel tubes were drilled, a logistical and technical masterpiece. Dams such as the Three Gorges Dam in China, which supplies enormous amounts of energy but also changed entire landscapes, had similar dimensions. Engineers also set global standards in the transport sector.
High-speed trains such as the Shinkansen in Japan or the TGV in France showed how technology could revolutionize travel. Airports such as those in Hong Kong or Dubai became hubs in a world that was more closely connected than ever before. Container ports and logistics centers transformed world trade into a machine that ran to the rhythm of engineers. These projects reflected not only technical ambition, but also economic and political developments. Globalization meant that engineers increasingly worked internationally. Experts from different countries cooperated, standards were standardized, technologies were disseminated worldwide. Engineering firms planned bridges in Asia, power plants in Africa, stadiums in South America. The profession became global, and so did the successes. But mega projects also have their downsides. They devoured enormous sums of money, led to massive interventions in the environment, and posed ethical questions for engineers. Was it justified to resettle entire villages for a symbolic project? How could you ensure that progress benefited not just one elite, but everyone? These questions began to shape the self-image of engineers. The late 20th century made it clear that engineering was no longer just a tool of national power or an expression of scientific curiosity, but became the engine of a global culture. Bridges, skyscrapers, tunnels, and dams are not only technical structures, but also symbols of a world that has moved closer together. Engineers thus became the designers of an epoch in which the local and the global are inextricably intertwined. Her works are the visible monuments of globalization, monuments made of steel, glass, and concrete that show how technology connects the world.
Chapter 19. Engineers and Sustainability. Energy Transition, Recycling, Environmental Technology. In the late 20th and early 21st centuries, a new topic came to the fore that permanently changed the self-image of engineering: responsibility towards the environment and society. While the decades before had been characterized primarily by the belief in unlimited growth, it now became increasingly clear that technical developments also had a dark side: air pollution, climate change, resource scarcity. Engineers have had to face new tasks, not only to create progress, but to make progress that is sustainable. A central field is the energy transition. Since the oil crises of the 1970s, it had become clear that fossil fuels would not be available forever. At the same time, rising CO2 emissions are making the consequences for the climate visible. Engineers began to develop alternative energy sources and make them usable on a large scale. Wind turbines grew from small mills to gigantic wind farms whose rotors are larger than aircraft wings. Photovoltaic systems have become more and more efficient and cheaper, so that today they cover roofs and entire landscapes. Hydroelectric power plants were modernized. Geothermal energy and biomass supplemented the energy mix. At the same time, a new field of research emerged: energy storage. Engineers developed batteries, pumped storage power plants, and hydrogen systems to compensate for the fluctuating availability of renewable energy. Smart grids now control the flow of energy in real time. These are all solutions based on engineering precision and creativity, and which are crucial to tackling the climate crisis. Recycling also came into focus. While previous generations often simply landfilled waste, engineers today are looking for ways to keep materials in the loop. Metals, plastics, glass, and paper are collected, sorted, and processed. Modern recycling plants use sensors, magnetic fields, and robotics to efficiently separate materials. At the same time, new materials are being created that are easier to recycle. Engineers are at the forefront of making the circular economy a reality. Another field is environmental technology. Wastewater treatment plants, filter technologies for factories, catalytic converters in cars, these are all products of engineering developments that help to reduce the pollution of air, water, and soil. Engineers are working on methods to filter CO2 from the air, rid oceans of plastic, or remediate soils.
Protecting the environment has become as important a task as building bridges or machinery. At the same time, thinking in the construction industry is changing. Today, sustainable construction means constructing buildings in an energy-efficient, resource-saving manner and in harmony with the environment. Engineers are planning houses with solar facades, heat pumps, rainwater harvesting, and recycling materials. Entire cities are designed as smart cities, in which technology, the environment, and quality of life are to be in balance. The role of engineers thus changed fundamentally. They were no longer just the engines of progress, but also guardians of sustainable development. Their responsibility now extended over generations. Decisions about materials, energy sources, or construction methods influence not only today, but also the world of tomorrow. Of course, this path remains full of challenges. Sustainability often means compromises, higher costs, longer development times, technical uncertainties. But engineers have proven time and time again that they can find solutions when the pressure is high enough. The energy transition, recycling, environmental technology, they all show that engineering is capable not only of reacting to problems, but also of actively shaping new paths. At the beginning of the history of engineering, there was man who dug canals to irrigate fields. Today, thousands of years later, engineers are faced with the task of protecting the entire ecosystem of our planet. Their tools have changed, their responsibility has grown, but the basic idea remains the same. Technology should secure and improve people's lives.
Chapter 20. Outlook: The Engineer of the Future. AI, Robotics, and New Horizons. The history of engineering is a history of constant change. From the first canals in Mesopotamia to the pyramids of Egypt, the bridges of the Romans, the cathedrals of the Middle Ages, the machines of industrialization to space travel and the digital revolution, engineers have always pushed the boundaries of what is possible. But the most exciting question is, where does this path lead in the future? New horizons are already emerging today. Artificial intelligence is changing engineering in all areas. Computer programs are now able to independently optimize designs, perform simulations, and learn from data. Engineers work together with AI systems that can not only perform calculations, but also make creative suggestions. The role of humans is shifting, from pure designers to designers and decision-makers who cooperate with intelligent machines. Robotics is another field that will shape the future. Robots are already taking over tasks in factories, on construction sites, or in the operating room. Engineers are developing machines that can work in hazardous environments, disaster zones, on the bottom of the sea, or even on distant planets. Autonomous systems such as self-driving cars show that engineers not only have to combine mechanics and electronics, but also have ethics, safety, and society in mind. Space travel also remains a major topic. The Moon is once again the destination of international missions, and Mars is within reach. Engineers are faced with the challenge of creating habitats in space, securing energy supply, and recycling in extreme conditions. Perhaps 21st century engineers will build the first cities beyond Earth, a task reminiscent of the first builders of Mesopotamia, only on a much larger scale. Sustainability remains a basic condition. Engineers of the future must find solutions that preserve the planet. New energy systems, sustainable materials, closed material cycles. Cities could become green metropolises in which nature and technology are closely intertwined. Buildings that generate energy instead of consuming it, factories without waste, transport without emissions. These are visions that engineers are already designing today. Digitization and networking open up additional dimensions. The Internet of Things connects machines, houses, vehicles, and entire cities. Engineers design systems that exchange data in real time, control traffic flows, and optimize energy consumption. The line between the physical and digital worlds is blurring, and engineers are the bridge builders between the two.
But with all these possibilities, the questions of responsibility are also growing. Engineers of the future must not only be technically brilliant, but also act in a socially sensitive manner. Who do their inventions serve? Who bears the consequences? How can progress and justice be reconciled? History has shown that technology can both liberate and destroy. The future of engineering depends on whether we succeed in using this power responsibly. The engineer of the future is therefore more than a technician. He is a researcher, designer, mediator, sometimes even a visionary. He works in teams that are networked across continents and disciplines. He builds not only machines and structures, but entire systems that combine the environment, society, and technology. If we look back in history, we see that engineers have always achieved great things where they had the courage to try the impossible. This attitude will also determine the future. Whether it's healing the planet, conquering space, or designing digital worlds, engineers will be the architects of a new era. The history of engineering is not complete. It starts anew every day, with every idea, draft, every screw that is turned, every algorithm that is written. The outlook shows that the journey continues, and it remains more exciting than ever before.